Hi everybody, we are back and we are at our last problem set of the semester. I know. Everyone is so sad and we want to continue working, but again, this will be the last essentially problem set. It will cover corrosion and then you will also have to, on your exam, basically cover polymers as well. So that'll be one topic where we don't have a problem set, but luckily we have practice exams to kind of go over and cover those topics. So let's go ahead and get started today. So we are looking at this electrochemical cell, 5 materials, Cu, Pb, Sn, nickel, cobalt, standard conditions, i.e. room temperature, 1 mole of own solution, and atmospheric temperatures. Look at the table below, describe where electrons are flowing, and let's go ahead and start this one. So I'm going to create a new notebook. Actually, let's just exit this guy out. Let's do new notebook. I'm going to clear all of my kernel. And again, if we're at standard conditions, I know essentially that reduction reaction that can occur. So what are my materials? So Cu is equal to, let's go ahead and look on here, 0.34 volts. My Pb is equal to minus 0.126. What else? Cu, Pb, cobalt is equal to minus 0.277. Unfortunately, cobalt will probably be one of the unfortunate cause of a war because of lack of scarcity. Anyways, we don't need to talk about that on this. We can focus on, and then Sn, and then I think that's pretty much it. So tin is going to be minus 0.136. Perfect. All right. So whenever I'm looking at my E naughts, I do my cathode minus my anode. So Cu minus Pb. Agree with that. Pb minus Cu. I don't agree with that one. Cu minus E naught. Co minus Ni. Sn minus Pb. Co minus Pb. And Sn minus Ni. So these are where our electrons should be. These are actually the correct values. So there's some issues, as you can kind of see in this cell. So we know that the electrons are moving from the anode to the cathode. Anode to the cathode if this value is positive. So here, the material is not moving from the anode to the electrons aren't moving from the anode to the cathode, they're going in the opposite direction. So, for example, in this first problem, Cu, Pb, electrons are moving from Pb to Cu. Here, they're not moving from the anode to the cathode, they're actually moving from the cathode to the anode. So you can do the same thing for CO, moving from CO to Cu. CO and Ni, it's actually moving from CO to Ni, and vice, et cetera, et cetera, et cetera. So, and we can kind of tell, again, the material that will corrode is the one that is losing electrons. It is the material that is undergoing oxidation, and it will be less noble. So the more noble will be essentially those values. Excellent. So, and then the full cell reaction. So, for example, if we're looking at this CuPb, so Cu is initially in its ion state and is gaining 2 electrons because, again, electrons are flowing from anode to cathode for this particular reaction, just like we kind of saw previously, and it's going to form Cu. For Pb, we start as Pb and then we undergo oxidation, so we lose, so Pb 2 plus 2e minus. I add my products and reactants, my 2 e's cancel out, and I'll get Cu 2 plus Pb goes to Cu plus Pb 2 plus. So that would be my full cell reaction. And then again, if I'm looking at my Nernst equation, E minus E naught equals this thing minus, we'll look at it here. Let's get our good old friend the Nernst equation. Nernst equation at our disposal. So, again, the Nernst equation is for non-standard conditions, so we'll show actually that right here that we are working with. So it's going to be minus RT over NF, the natural log, again, of my products, which is my Pb, so basically my anode over my cathode. So the concentration of, again, the activity. So the molar concentration. So if this is 1, if they're equal to one another, log of 1 is 0, and E is equal to E naught. E naught is what we have been calculating here at our standard conditions. The E here is at our non-standard conditions. So what if I change temperature or concentration? Will this change the measured potential? Yes. How can I change which material will corrode? Well, I could actually change temperature or I could change compositions. How do I know if the reaction occurred spontaneously? Again, if if I know that actually, I could use this equation, delta G equals minus NFE. So depending on, again, the E that's measured, we can make this reaction either be spontaneous, i.e. delta G is less than 0, or non-spontaneous. So if my E becomes, basically positive or negative, then I could switch it. All right, calculate the electrochemical potential of all 7 experiments. If we are now working at room temperature, so let's go ahead and start to solve this. So this is going to be I'm going to call this E01, E02, E03, E04, E05, E06, and E07. I'm going to make a list just to make this. So E0L is equal to E01, E02, E03, E04, E05, E06, E07. So I am also assuming what else do we have in here? So our temperature is room temperature, so T is equal to 298. Our Faraday's constant is equal to 96485. If the number of electrons or moles of electrons is going to be, N is going to be equal to 2. Our gas constant is 8.314. Make sure all those units are correct. My anode, so Ca is equal to, let's see. Okay, we're just calculating that electrochemical. So Ca is going to be equal to 0.1. C concentration of my cathode is going to be equal to 0.9. And we need to figure out again. So we'll figure out for copper and Pb what corrodes, what does not. So my Nernst equation is just essentially going to be actually this is a table. So it's going to be, because usually my Gibbs, or actually my Nernst equation is E minus E naught. So I'm just going to move E naught to the other side. So that's going to be a plus. So it's going to be table minus R times T divided by N times F times, again, this is probably fine, but the log of Ca divided by Cc. And then I'm going to do plus E naught L, and then I'm going to just pull out each of those values, I from 1 to length of E naught L. And these would be my values. Now, we're asked for this particular, for CO and PB, i.e. equation number 6, what would be the temperature at which this switches? So E naught 6 is going to be positive. So we need to figure out when is E, our Nernst equation potential, going to be 0. So I want to solve 0 minus E naught 6, set it equal to this equation, but I am going to keep temperature T1. So let's just solve for that. That's quite a high temperature. But again, you can increase temperature and you could change which material corrodes and that doesn't corrode. Excellent. Now we're working in the booming industry, which involves creating underwater luxury homes. To do this, we have to run some piping. We're thinking of using copper, or actually not copper, cobalt. Again, we have to use metal in contact with, so it won't corrode. We have the following candidates, AU, PT. So again, we're going to do kind of the same procedure here. Which one will work, which one will corrode, prove quantitatively using standard conditions to start with, for each where electrons will flow, et cetera, et cetera, et cetera. So we can kind of continue with this. So we still have Sn, so we need PT. So let's go ahead and let's find these values here. So let's go ahead and look at it. Let's keep moving here. So Sn, so we need AU is going to be equal to 1.4. PT, I believe, no, we don't have PT, is going to be 1.2. Cu, we already have. Mg, we definitely don't have. That's going to be very negative because it wants to give up electrons, 2.363. What else do we have here? Mg, zinc, we don't have that one. Zinc, equal to Zn equals minus 0.763. You may have this already set up for your exam, or at least I would consider it. Fe is equal to minus 0.44. What else? CD equal to minus 0.403. So we should hopefully, do we already have CD? No, we don't. Minus 0.403. Excellent, excellent. So CD and then SN we have and PB we have. So we can start to do this experiment. So again, we're trying to figure out, again, if it will corrode. So I'm going to set up my, we want to make sure in this problem, we need to make sure CO does not corrode. So CO has to be basically our cathode material. So if I set that as my cathode, so CO minus AU, this is negative, so electrons are flowing the other way, so this will not work. So CO will corrode. So if it's negative, it is going to corrode. So CO minus PT, that will also corrode. CO minus Cu, that will also corrode. CO minus Mg, that one will actually work. CO minus Zn, that one will work. CO minus Fe, that one will also work. CO minus Cd, that one will work. CO minus Sn, and CO minus PB. So COSN won't work, PB won't work as well. So now we can do what assumptions make. Again, we're assuming we're at standard temperature pressure conditions. So the temperatures, calculate temperatures, we can switch which material corrodes. So again, we're going to do essentially the same thing here. And now we can go ahead and get started. So let's figure out the temperature at which this changes. So we could utilize actually quite a bit of this code here. And what we'll do simply, we'll kind of make this hopefully A, so let's paste this code in here first. A, B, C, D, E, F, G, H, I. So we'll just shift enter all of these. Shift enter, we'll make a table again. So state list equals A, B, C, D, E, F, A, B, C, D, E, F, G, H, I, J. Okay, so we're here. Okay, so that's our E naught. Now we know our Ca, our anode, concentration anode is 0.15, cathode is 0.85, and it's in its own ions. And then we're asked the temperature where it switches. So E naught minus list I. Actually, I'm going to do J table from J goes from 1 to length of the list. And there's your temperatures. Excellent. So, told my undergrads to create a sacrificial anode in order to protect. So I need to protect CO. So I've got my CO when connected to Cu. So I know that, again, at my standard conditions, I need to pick basically, draw one possible configuration and identify. So I need something that's going to be less electronegative. So actually, something that really wants to give away electrons. So if I look at cobalt, I could put anything in between here for cobalt and copper. I could do CuD, that would be not really effective. Fe, Cr, Zn, Al, Mg, and even potassium. So these would be my ideal candidates here. This would not be the most effective, but it'll still work. So anything that has a lower electronegativity than cobalt. That's it. Last problem set. So study well for your exam, and then I hope to see you in a future class. Thanks. Bye.